Okay, problem 3. Determine the carburizing time necessary to achieve a carbon concentration of 0.5 weight percent at a position 2 mm into a carbon alloy that initially contains 0.2% weight percentage carbon. The surface concentration is to be maintained at 1.3% weight percent carbon, and the treatment is to be conducted at 1000 degrees centigrade. So use the diffusion data for gamma iron in table 5.2. Okay, so in this problem you have some concentration data with respect to the time and position. Okay, so let me draw a line. This line represents the position. Okay, so say this is an x-axis, okay, line, and this is the surface. Okay, so surface position I represent by 0, and the point for which we want is 2 mm into the surface. Okay, so I take it as 2 mm point. So, and let's take the time over here, time over here. So at a time of 0, the concentration at 2 millimeter into this carbon alloy, this concentration is 0.2%. okay, 0.2% by weight, and at some time t, this concentration will be 0.45%. 0.45% after some time t. Okay, so this time we need to find, and the condition is that the surface concentration is maintained at, whether it is at time 0 or at time t, the surface concentration is to be maintained at 1.3%. okay, so this is the approximate scenario in this case. Anyway, in terms of the symbols, so surface concentration is represented by CS is 1.3%. okay, by weight percent, the initial concentration is 0.2%. okay, and the concentration which is which is to be achieved is 0.45%. so this is represented by Cx, 0.45 weight percent. okay, percent weight or weight percent, well, actually the normal convention is weight percent. So now we know that Cx minus C naught is equal to divided by Cx, Cs minus C naught. Is equal to 1 minus ERF over x divided by 2 into 2 under root dt. So where ERF is the error function, so this is a mathematically integral function. The exact solution of that function is quite complicated, so we have the ERF error function table, so its approximate value can be found from those tables. So now we can put the values into this equation. So the values are Cx is 0.45 minus C naught is 0.2 divided by CS is 1.3 minus 0.2 is equal to the same value 1 minus ER F x over 2 under root dt. So this left hand side will be equal to 0.7727, and then if you will simplify it, it will become ERF will be equal to 1 minus 0.2273, which is equal to 0.7727. Okay, so this ERF so this ERF value can be found from the table. So the table gives us the values of ERF of a function z. Okay, this values give, so we can equate it to 0.7727, so where z will be equal to x over 2 under root dt. Okay, so we have from the table we have the values for ERF of z. So ERF of z, we have these values from the table for various values of z. So for example, we have the values for various z, this error function values, something like this. So we can take the value of because the values around 0.7727. So just before 0.7727 there is a value of 0.7707 at a value of z equal to 0.85, and just above over 0.7727 it is 0.7970 for a value of z is equal to 0.9. So in this case our required value of z will be between 0.85 and 0.9 because we need an error function value equivalent to 0.7727. So this can be calculated by the linear interpolation. So for this linear interpolation you take a difference of z with 0.85, z minus 0.85, and divide this by 0.9 minus 0.85 whole value, 0.9 minus 0.85, and then similarly you can take a difference of 0.7727 minus 0.7707, okay, divided by 0.7970 minus 0.7707. Okay, so from here you can calculate the value of z, which will be equal to 0.854. So now we know that z is equal to x over 2 under root dt, where d is the diffusion coefficient. So in this case we don't know the value of d, t we want to find. So the value of this diffusion coefficient can be found from this equation. Okay, let me correct it. This equation is QV over here. So where d naught is the diffusion pre-exponent and QV is the activation energy. So the values of d naught and QV can be found from table 5.2. So d naught from table 5.2. In the table 5.2, the values are given for various combinations. So in this case, we are talking about carbon in gamma iron. Okay, so for carbon in gamma iron, the values of D naught is given as 2.3 into 10 to the power minus 5 meter square per second, whereas the activation energy QV is given as 148,000 joules per mole. So this is for carbon in gamma iron. Okay, so if we input these values into this equation, and by the way, K is the gas constant, which is 8.31 joules per mole Kelvin, and T is the temperature is 1000 degrees centigrade. Okay, and then we need to convert it into the kelvins. So 1000 degrees centigrade plus 273, which will be 1273 Kelvin. So now this is just a matter of inputting these values into this equation and calculations. D will be equal to, diffusion coefficient D will be equal to, after you will input these values, it will be equal to 1.93 into 10 to the power minus 11 meter square per second. And now we can put these values of D into this equation. Z is equal to, so now we know that since Z is equal to x over 2 under root dt. So you can put now we know the value of Z is equal to 0.854 and x is equal to 2 into 10 to the power minus 3 and over 2, and then D is 1.93 into 10 to the power minus 11 and multiplied by t. Okay, and then solve it for t, then t will be equal to 7.1 into 10 to the power 4 seconds. That means 71,000 seconds, which is equal to 19.7 hours. Okay, so it will take 19.7 hours for the concentration at a 0.2 millimeter into the carbon iron alloy to increase from some values, to increase from 0.2% to 0.45%, with the condition that the surface concentration is maintained at 1.3%. Anyway, it's a long statement, but I hope that we understand the context of this question. Thank you.